Our Back to Basics series. Today's episode is titled Into the Ingress Abyss, Understanding Leaks, Causes and Consequences, Part 1. I'm Brady Volpe, founder of the Volpe Firm and Chief Product Officer at OpenVault, here once again to navigate these intricate waters of cable technology. And as always, I'm joined by the ever-knowledgeable Ron Hranac, our go-to expert when it comes to demystifying complex topics. Our last deep dive was an enlightening journey, and today we're shifting our spotlight to Ingress. We'll be unlocking the secrets of signal leakage and diving deep into direct pickup and breaking down the terminology to make it all crystal clear. Whether you've been in the cable industry for years or you're just dipping your toes into these technical waters, we've got insights and explanations that promise to broaden your understanding. As tradition, Ron needs little introduction, but for newcomers, do check out his extensive bio in the description below. So without further ado, let's embark on another exciting episode with the incomparable Ron Hranac. Ron, as always, a pleasure to have you sharing your wisdom with us.
Thanks, Brady, and happy Friday to you, and happy Friday to everyone who is joining us live today. As Brady noted, the subject is signal leakage, ingress, and direct pickup. And these are topics very, very familiar to many of you who have worked in the industry for any length of time. And for those of you who are new to the industry, I think you'll pick up some good tidbits of information on just what the fuss is all about when it comes to signal leakage and ingress and direct pickup interference in our networks. It basically means RF is going where we don't want it to go. And that could involve going out of the plant or coming into the plant. Or some of the devices we have connected to the plant. So with that, let me share my screen.
Thanks, Ron. While you're sharing, I'm really excited I think is going to be a great topic, Ron. You've got amazing visuals in this, so please like and subscribe if you're watching. The visuals are awesome. The topic is fantastic. If you're a tech in the field, you're probably battling ingress all the time. If you're in management, you're probably wondering why techs are spending so much time battling ingress. And if you're a subscriber, I think this will be really enlightening to you because I talk a lot about in-home wiring, making sure you're not messing with your wiring as a subscriber, or if you're trying to repair your wiring. You're going to see a lot in this presentation that Ron has to help you understand why home wiring is so important to making sure that your modem is working, as a tech to understanding why wiring is important. The visuals are just going to say it all. So, Ron, take it away.
Well, thanks. And there's a nice screenshot on the opening slide here to the PowerPoint deck that shows I think a pretty nasty example of ingress in the return path of a cable network. You can see the four cable modem signals there, and then you can just see a really nasty looking noise floor that's got all kinds of noise and other interferences getting into the return path. Of course, that's just one part of what we're talking about today. This, ingress is certainly a big piece of the world related to the shielding integrity of our networks, but the other part is signals going the other way, leaking out of the network, which we definitely don't want to happen because that can result in all kinds of things. So let's start with some of the terminology that we use here. And ingress, of course, is the unwanted entrance of over-the-air signals. And by that, I mean discrete RF signals such as shortwave radio and ham radio and CB and even over-the-air noise sources. But getting into a cable network, and that happens because of a degraded shielding effectiveness in the coaxial cables and connectors and other pieces and parts of the network. It's the opposite of signal leakage. Now, I've got a little note here that's kind of a subcategory of ingress, and that's direct pickup interference. Direct pickup is similar to ingress, except the over-the-air signals get into a susceptible set-top box or cable modem or TV set or piece of test equipment or other device directly without any cables or anything connected to that device. If the susceptible device's outer case is not properly shielded, then the inside wiring inside that device or the printed circuit board traces or other components can act like antennas and directly receive interfering over-the-air signals. And that can be an issue, particularly with some older devices, as we'll talk about a little bit later. Signal leakage, that's the unwanted emission of RF signals from the inside of a cable network into the over-the-air environment. And here too, it's caused by degraded shielding effectiveness of the pieces and parts of our network, the cables and connectors and other components. This is also called egress, although I think most people just call it leakage. One thing it is not is CLI, and I've talked about this in the past. Signal leakage and CLI are not the same thing. You cannot measure CLI, you can't test CLI, you can't fix CLI. You have to measure leakage in order to calculate CLI. So we're talking about signal leakage here as a subset of all the material that's in the presentation today. So what the heck causes ingress and leakage? Well, if we think about the nature of our networks, the coaxial cables, the connectors, adapters, the passives, the actives, all the pieces and parts of our distribution network and our subscriber drop provide a nice shielded transmission medium that is independent of the over-the-air environment. Now, the over-the-air frequencies are allocated by the government or governments, government agencies, to various services. So think broadcasting and two-way radio communications and so on. But cable operators, for the most part, are able to enjoy the ability to use frequencies inside of the cables, which are closed networks or are supposed to be, as they see fit. Now, there are some countries that do not allow use of certain frequencies in cable networks, but that's not the case in the US. Cable operators are welcome to use whatever frequencies they want or are able to use, but as long as the cable network is nice and tight and signals aren't leaking out and over-the-air signals aren't leaking in, we can take advantage of this thing called frequency reuse because of the fact that our network is a closed transmission medium, at least it's supposed to be. So that means we can use signals and frequencies inside the cable network that are completely different than what may be on the same frequencies in the over-the-air environment. So the cable industry has taken advantage of this thing called frequency reuse pretty much since day one of the industry's existence, going all the way back to the 1940s. So what causes leakage and ingress? Well, it all boils down to the shielding integrity of the network being compromised for some reason. And there are all kinds of reasons, and I'll show you some examples a little bit later on. And when the shielding integrity of the network is compromised, then signals inside of the network can leak out into the over-the-air environment and potentially interfere with licensed over-the-air services. So that's not a good thing. And you see graphically here, signal leakage being represented by these red curved lines emanating from the cable network and potentially interfering with, let's say, a cell tower or similar. Now, going the other direction, those over-the-air signals can leak into the cable network through compromised shielding, whether it's a cracked cable or loose connector or whatever, and then that can cause interference to signals inside of the cable network, which of course is something that we don't want. So let's look at signal leakage interference. What is it? The what is that signals inside of the cables leak out, causing interference to over-the-air services such as long-term evolution. And then it can also interfere with broadcasting or two-way radio or other services. But the signals inside the cable are leaking out and causing interference to over-the-air services. Well, how? Well, the shielding effectiveness of the cables and the components, and by components I mean the connectors and passive devices and active devices, are degraded for some reason. And why is this important? Well, if the signal leakage results in what's called harmful interference, which is defined in Part 76 of the FCC rules, then interference can occur to over-the-air users, and you can get in big trouble with the FCC as an example. And that can result in warnings or in severe cases, fines, and in really bad cases, the FCC can force you to shut down the interfering signals until the cable plant shielding integrity has been repaired. And yes, if you look in Part 76 of the rules, you'll see that the FCC has the authority to do that. So that's a pretty good reason why it's important to pay attention to signal leakage performance of your network. Looking at the graphic on the screen here, this was taken from an over-the-air test that I did actually quite a few years ago. But here you can see a bunch of leaking single carrier QAM signals. They're present in the over-the-air spectrum, and this happens to be in the 698 megahertz to 806 megahertz spectrum. At that time, that was cellular and LTE. The bands have since expanded, but you can see the leaking QAM signals. But you can also, in this case, near the center of the screen, see Verizon's downlink signal coming from the tower and going to the user equipment, such as smartphones. And over a little bit to the right of that, you can see public safety radio communication signals in the over-the-air environment. And note what's right underneath the public safety signals, a leaking QAM signal. And we don't want that. We do not want signals inside our network leaking out and causing interference with over-the-air services. So ingress interference is the other direction. So the what is over-the-air signals leaking into the cable network. And how? Well, the shielding of effectiveness, as before, of the cables and components are degraded for some reason. And so why is this important? Well, the main reason is that that interference to the signals inside the cable network can occur when over-the-air signals and over-the-air noise leak into the network. And that, of course, is something that we definitely don't want. So here's an example of ingress interference in the outside plant. So the example is a cell tower. It's transmitting its normal over-the-air signals, but note here at this utility pole in the upper screenshot here, there's a crack in the cable, and ingress can get into the network through that degraded shielding, in this case, the crack in the cable. Down below on the bottom half of the slide, we can see a full band capture from a cable modem that shows the downstream spectrum. And we've got several things visible here. We can see amplitude ripple in the spectrum, which says, hey, there's an impedance mismatch somewhere. But note the presence of over-the-air FM broadcast radio signals getting into the network. So this is actually getting into a subscriber drop or the hardline plant, but showing up in a cable modem's full band capture. And that's over on the left side of the display. We can see LTE ingress at the upper end. And then beyond the upper end of the downstream spectrum, you can see two-way radio and cell signals. Those shouldn't be there. That spectrum should be nice and clean. But here we can see a really good example of downstream ingress interference to the cable network. And it may well be that the location where the ingress is getting in, that might be causing the impedance mismatch that's in turn causing the amplitude ripple seen across the top of the spectrum.
Ron, this is a beautiful image, and I just want to touch on this for people who may not know. Now, coax cable, it's not designed with cracks in it. Is that correct? I mean, how does this happen?
I've never seen it designed with cracks. It's supposed to be crack free, and the shielding integrity of the coaxial cable when it comes from the manufacturer is actually quite good. Hardline cable on the order of 140 dB or better. At least in years past when I used to do lab testing, that was the limitation of the test equipment setup that we were using to test shielding integrity. It was 140 dB, which is pretty crazy. And then drop cables, depending on whether it's dual shield, tri-shield, or quad shield, can be somewhere in the 90 to 110, 115 dB shielding integrity range. But no, there shouldn't be any cracks in that cable when it comes from the manufacturer.
Right.
In this case, I would suspect that the cable was installed incorrectly. The example you see up here, probably insufficient sag in the span between poles, incorrectly formed expansion loops or a combination of the two. And over time, as the cable expands and contracts with temperature changes, you see cracks forming in the shield. In this case, at the utility poles, or sometimes the cracks will occur right in the expansion loops because of the improper amount of sag in the span between poles.
Yeah, and so I think, thanks, Ron, for clarifying. And I think that's an important takeaway from this is, if the cable plant doesn't have damage, if the coax doesn't have damage like that crack Ron saw, and the connectors are all properly connectorized, we shouldn't have this leakage and the ingress and egress that we're talking about. And Mia, if you could put that comment up there from Sean. So Sean Lester, thanks for joining today. Sean and I know each other as well as a lot of other people that join in the chat room. So there's a lot going on in the chat, but Sean says, I believe public safety interference will bring the wrath of the FCC faster than any other interference. And I know Sean does a lot of work in this area, so appreciate the comment there, Sean. So Ron has mentioned the FCC, and as operators, you may not have the FCC, you may not have problems with the FCC, but I think Sean's comment is relevant. That it's if you have ingress or egress coming out of your plant, Ron will correct me here if I say it wrong, but when your signals start to interfere with public safety and they see the signals coming in, that's when they may, basically when you start interfering with someone else's service, that's when they may call the FCC, and then the FCC is going to come looking for those signals. And Ron could probably tell you more about how that whole process works.
Oh, yeah, and it's not just public safety. when Verizon and AT&T started rolling out their LTE services back around 2010 or so, their engineers started noticing these 6 megahertz wide QAM haystacks getting into their cell towers. And they said, what the heck is this? And they tracked it down to leakage from cable networks. And of course, they'd contact the cable operator, and the cable operator would take their leak detector out there, which in those days could only measure stuff down around 130 megahertz. They'd say, well, there's no leakage at 130 megahertz. And the operators didn't have a way to measure leakage up around 600 megahertz. And so the field engineers from the cell tower companies would show them on their test equipment, say, here's your leaking QAM signals. And of course, since then, the test equipment manufacturers have given us, as an industry, digital compatible leakage detectors that work on multiple frequencies, which is good. But there were some instances where cable operators didn't go out and fix their leakage that was interfering with cell towers, and the FCC fined the cable operators. I remember looking on the FCC website several years ago and seeing the names of several well-known cable companies that got some nasty fines from the FCC for leakage that caused interference to cell towers. Yes. So that's something that you want to avoid.
It's no joke. The FCC will come after you if you cause interference. So I think a good comment, Sean. Thank you.
Yeah, very, very good. All right, downstream ingress. We hear the term ingress. We tend to think more commonly about the upstream, but downstream ingress can be an issue too. And it typically shows up as interference to analog TV channels, if you still have it in your networks, and of course the digitally modulated signals. And the typical sources for downstream ingress include two-way radios. So think two-way police, fire, taxis, so commercial stuff, ham radio, and so on. Local TV and FM broadcast signals, LTE downlink signals, that would be from the tower to user equipment, and LTE uplink signals, so the user equipment, like your smartphone, to the tower. All those things can get into the downstream spectrum and cause problems and interference to the cable network. And understand that it is not the fault of the signal source. The fault is not the broadcaster. It's not the ham radio operator. It's not the LTE tower. It is your network not being properly shielded and allowing these signals to get in to the plant. So you don't go after the operator of the service whose signal is interfering with your spectrum. You go out and find out why that signal's getting into your network and fix the problem there. Now, of course, upstream ingress, that's what most of us are familiar with, and that the sources for that can be any number of things: shortwave broadcast, aeronautical, maritime, government, military communications, ham radio, CB, impulse and burst noise, power line gap noise, vehicle ignitions, neon signs, static from lightning, power line switching, transients, and the electric motors, and Part 15 devices, and switch and on, and grow lights and ballasts. All these things can be sources of ingress in the upstream spectrum. Well, guess what? Same thing. The problem is not the source. The problem is that this stuff is getting into the network through a compromised shielding integrity of your network. That interference can be in channel, but keep in mind that ingress interference in the upstream at other frequencies, even frequencies where you don't carry upstream signals, can cause laser clipping. And one place that many operators don't think about looking is below 5 megahertz. We tend to think, well, the upstream starts at 5 megahertz. But if you look below 5 megahertz, you may see that AM broadcast radio is getting into your upstream and is severe enough to cause laser clipping in the nodes. So look below 5 megahertz, because this stuff can be on frequencies that are not necessarily the same frequencies you're carrying in your network. But of course, laser clipping affects everything in the upstream. So when it happens, you got to find out where that stuff's getting into the plant and fix it.
It's also cumulative too, right, Ron? I mean, you can have just a little bit of noise, but as that noise starts to add up, it's the sum of that noise that can cause laser clipping.
Well, the reverse funneling effect is a big gremlin. In many cases, ingress gets in through a lot of low-level points. And ingress in one, let's say getting into a drop, might be fairly low level and not enough to cause interference. But if that ingress is getting in multiple locations and it funnels back toward the node, it can become a lot stronger back toward the node, and then you've really got problems.
Yep.
So here's a glance at an NTIA frequency chart that just covers the 5 megahertz to 30 megahertz spectrum. And this shows how frequencies are allocated to different services. And you can see there's broadcasting, that would be shortwave broadcasting, and maritime mobile, and there's fixed and mobile and all kinds of stuff. So the upstream spectrum is used for a lot of different over-the-air services. And all it takes is a cracked cable or loose connectors or something else for these services to get into your return path.
And I think so often we just say, oh, citizens band radio, CB radio, that's at 17 megahertz. We often think there's just one source of noise in the return. But I think that screenshot you just showed is important for us to recognize. The return is used for so many different over-the-air communications channels that there's lots of places that noise is going to get into our return.
Now, right
for
up here on
communications.
the lower right is citizens band radio. It's around 27 megahertz. And I'll often hear from techs who will say, well, that CB operator must be transmitting with an illegal amplifier. And maybe not. It doesn't matter. If the signal's getting into the network, you need to find out where it's getting in.
You got a leak in your network.
Well, and surprisingly, a 4-watt signal, which is the legal limit for a citizens band radio transmitting AM, it's 12 watts peak envelope power for sideband, but I don't think too many CBers use sideband. But that 4-watt signal, if it's, let's say the antenna's 50 feet from the cable network, I did an article in Communications Technology years ago and did the math and showed that a 4-watt CB radio could produce something like 50,000 microvolt per meter field strength 50 feet from the antenna. Yeah. And if that's next to a loose F connector or something, yeah, it's going to make you think that the guy's using an illegal linear amplifier when in fact he's not.
Yeah. That's 4 watts considering the modem's transmitting in milliwatts, in like 40 milliwatts compared to 4 watts.
Well, and think about downstream signal levels. 0 dBmV is 13 nanowatts, 13 billionths of a watt. So the power levels in our network are pretty low. Now, anecdotally, the cable industry's found that on average about 95%, and this varies some, of the garbage that gets in the return path comes from the subscriber drop. So that says 5% comes from the hardline plant. So roughly 25% from the tap to the side of the house, and 70% or thereabouts from inside the home. Now, the actual percentages vary among cable operators, but this has been the anecdotal numbers that have been around for a long, long time.
And I get asked this question a lot, like, where do these statistics come from? Do we have anything that backs up these statistics? And I don't think there's really anything in the industry that says, oh, we've done an in-depth study, but I think you put it right. This is anecdotal. It's based on feedback of technicians and cable operators who have seen this data over and over and over again. Yeah. But I think you're spot on. We see this all the time, and I think these are very consistent numbers.
I think so too. Now, the screenshot on the right's kind of an interesting one. This one goes way back several years. When cable operators are just starting to play with two-way in many of the networks. And you can see the date on the screenshots, 1997. And in this particular case, the operator that captured this screenshot, and this was at the node or head end, I forget where, but they had gone out in the plant and put high-pass filters on all the drops. And so what's left here, you see that little rise in the noise floor over on the left side of the upstream spectrum there. That's coming from the hardline plant. Almost all the rest of it's coming from the drops. So they were doing some tests to see how well the network's shielding integrity is. And of course, you go out and start doing two-way service deployments. You got to take those high-pass filters out, and now you've got all those connected drops allowing garbage to get back into the return. But this was a good example of that. I think it kind of backs up the anecdotal numbers that most of that ingress gets in via the drops. So we think about the upstream spectrum in a cable network. What you see here, this is probably fairly typical. This is an older picture, but you can see there's just one upstream channel in this example. You can see a few shortwave radio signals over at the left. So this is not necessarily too bad. It's not ideal, but it's probably fairly typical. Not quite so good over here. That's that upstream noise floor is looking a little gnarlier. And then this one on the bottom. Okay, that needs immediate attention. That's really, really, really not so good.
Yeah, and I think that can really show us like the funneling effect. And so I just want to head over to the chat room for a second because Peter Vittman, welcome back, Peter, and thanks for everyone for joining. So Peter really is talking about the funneling effect here, and the resulting power, which can lead to laser clipping, is an interesting point because some operators only focus on the spectrum of the active upstream channels. And he's indicating that they have no interest in a noise lower than 25 megahertz. So I think, his point is it's really important to look at that noise below 25 megahertz, particularly if you have analog systems, as you had indicated, Ron, that's going to cause laser clipping. James Long, he goes on to say, he's got their people interested in looking at signals less than 25 megahertz by putting an upstream channel there. So lots of interest there.
Well, and there's the other piece, and you don't see it here. Note that in all these examples, the start frequency on the display is 5 megahertz. We're not seeing what's going on below 5 megahertz in any of these.
Yep.
And the ingress could be quite high there. And yeah, even though the bandpass of the network starts at 5 megahertz, it's not a brick wall. It doesn't, the response doesn't just drop off like a wall. It kind of rolls off gently. And if you've got a local AM radio station at, say, around a megahertz or so, and the signal's getting into the network someplace, that could be really, really strong. So I encourage people, look below 5 megahertz and see what's going on down there. You may be surprised.
And then just a couple more comments there. Jeremiah says that VOA seems to be the most prevalent return ingress in my market. Thankfully, it's 15 megahertz and lower most days, but we also have OFDMA channels there. And then Sean continues on, whenever I troubleshoot return noise, we start at around 1 megahertz and go all the way to 200 megahertz. So he's really looking at that full spectrum.
That's good. That's good.
Great practice, Sean.
Yeah, that's a great way to do it. All right, so where the heck does leakage get out and ingress get in? Well, there are all kinds of things. So this list is by no means comprehensive, but I think most of you will recognize things on here that are sources of ingress and leakage that you've probably run across on multiple occasions over the years. So poorly shielded customer premises equipment directly connected to the drop, inadequately shielded cable and equipment. This can be especially problematic near high power transmitters. Loose, damaged, or improperly installed connectors, adapters, splices, damaged cable shielding, and here the list can be quite extensive. So think abrasion. That would be, for example, hardline cable rubbing against a tree limb, or maybe even a drop cable rubbing against a tree limb. Yep. Burns, bullet and pellet holes, corrosion, cracks, cuts, rodent chews, staples through drop cable, and the list goes on. So anything that damages the shielding of the coaxial cable can be a source of ingress and signal leakage.
So much that can happen.
Oh yeah, and damaged RF gaskets on passives. So think line passives, splitters, directional couplers, power inserters, amplifier housings, node housings, faceplates. So if the RF gaskets get damaged or they're somehow missing, you're going to have leakage and ingress. Loose passive device faceplates, loose or warped amplifier housing lids, and this can be a big one. The manufacturers have, for as long as I can remember, provided tightening charts for the bolts on amplifier and node housing. So tighten them in a certain order and to a certain torque. And so many times in the field, I see the techs just wrench them down with drills that have got sockets on them, and they don't pay attention to the torque settings or the order that they're tightening them in. That can crack or warp the housing lid, and when that happens, you have no choice but to replace it, particularly if it becomes a source of ingress or leakage.
And I would say that's the rule in my experience, just driving them down with a socket driver. Most techs, I see that's what they do.
I shake my head, because every manufacturer has provided those diagrams, and it's like tightening bolts on a cylinder head on an engine. You got to do it in a certain order, and or even the lug nuts on the wheel on your car. You got to do it in a certain order and to a certain torque. If you don't, you're going to cause problems. And the same is true of active device housings, and to a certain extent, passive device housings. Retail grade cables. This is stuff that subscribers do. They'll go to the local big box store or someplace else and buy jumper cables and connectors and splitters and things. And in many cases, the shielding integrity of those things is just garbage. Cable Labs did tests several years ago. They rented a facility from the National Institute of Standards and Technology and tested a bunch of retail device components, and the shielding integrity was just awful. The stuff the cable industry uses tends to be pretty darn good. So in this bullet point, it's stuff that's installed by the subscriber, and you can have a really tight plant and do a really good job managing leakage and ingress. And when subscribers do this sort of thing, all bets are off. And then, of course, theft of service. Somebody hooks up an unauthorized drop, and it can really mess things up. And and potentially be a source of ingress or leakage. So here's some examples of shielding defects. And
These are beautiful.
yeah, these are many of these I've stole offline from some of the forums. So my thanks to the techs who posted these. Yeah. But these are all real world examples. You look at this stuff, so you can see rodent damage. There's a cracked shield here, a couple of the slides. The one over on the far right, say, yeah, who needs connectors? And more than likely, what happened here, this is probably in an apartment or an MDU, and somebody decided to steal service. So what they do, they just connect all the drops, right. And that way it makes it harder to figure out who is stealing the service. And I see one drop tag, and it looks like the rest of them don't have labels on them, so it can make it even tougher to find out who's doing what. But this is a good example of a really nice source of leakage and ingress. So,
yeah, there's no F connectors on there. I mean, that's really the big issue. There's just center connector going into the F connector or the F port and shielding, and that shielding's not attached to anything. So who knows what happens then?
This is not good. And I love this one on the left here. Obviously, a tech didn't have the right nut driver or something to tighten the faceplate on this passive, so he's used a zip tie to hold it in there. You look at that, just go, oh, come on now. If that's not properly tightened, the RF shielding gasket on that faceplate is not going to do its job. And it's also not going to keep the water out because that's not adequately tightened. So water's going to get into that passive. RF's going to leak out. RF can leak in. Big problem. The middle one shows an example, probably at an apartment building where a rodent of some kind got into the lockbox here. But notice the big hole on the side of the lockbox. Yeah. That's where a squirrel could get in, or a mouse or something. It's just chewed the daylights out of the cables here. So we got rodent damage on all these drops. Not good. Over on the right, this might be a subscriber that decided to try to fix the cable themselves. If they were digging in the garden or something, and inadvertently cut the cable with a shield. So, I've got a wire nut. I can use that. I mean, it works on electric wire. Why not on coax? So not good. Got a nasty impedance mismatch, an RF shielding issue there. So leakage and ingress.
Yeah, James Long in the chat is saying one on the far right is his bad. I'm not sure if it's this slide or the one before, but I think it's just funny. It's a good sense of humor, James. Appreciate it.
Oh, yeah. Now, over on the left, this is one of those things that might not be readily obvious, but as you look at it, you'll note that the center cable here is blackened. And in this case, it's a hot drop going to probably a house or a unit or something. And the likely culprit here is that the neutral in the electrical wiring for that house has come loose or disconnected or has somehow been damaged. And the subscriber drop cable is acting as a neutral conductor, and it's carrying more current than the cable is designed for. So that damages the cable, can melt the cabling, can cause damage to the shielding and be a source of ingress and leakage. Not to mention a safety hazard.
I was just going to say, let's just take a second and talk about the safety precautions that everyone should understand about a hot drop, and that can really be a danger to folks.
Oh yeah, and a lot of techs carry foreign voltage detectors with them, so they see something like this, they can do a quick check and say that's hot. The best thing that they can do is to contact the subscriber and say, you need to have an electrician come and look at your electrical panel, because likely there's a fault in your electrical panel wiring and probably in the neutral conductor or something.
And by hot, Ron's not meaning temperature hot, but he means that could be carrying 110 volt AC. So it could potentially kill you if you're not careful.
Well, yeah, it could be very, very dangerous. So that's something that needs to get an electrician involved. The center photo, same thing. We can see the cable has been damaged, and it's hot from two perspectives. Temperature wise, it melted the cable, but the hot may also be voltage that's present there that could be hazardous. And the picture on the right, I think that's self-explanatory.
That's the rat's nest.
That's kind of a rat's nest. I could probably go into a setup like that and find lots of loose F connectors and maybe some that are improperly installed. And that's almost certainly going to be the source of leakage and ingress in this is probably an apartment building or something, or a commercial complex. But a mess like that's just inviting trouble. How about this homemade splitter on the left? Now that somebody cut this out, and yeah, it'll work as a splitter. Of course, it's a nasty impedance mismatch, but there's no shielding there. So there too, you've got a nice place for leakage to get out and ingress to get in. Then the middle one, of course, yeah, the customer might say, well, the last tech left it like that. And you notice there's no connector on the, or at least well, maybe there is well, I can't tell if that's a crimped connector
It
on the
looks
back.
like a crimped connector
It
to me,
might
but
be a
yeah,
crimped
it's
connector,
tough to tell.
it
It
is
shouldn't
tough
be
to
like
tell,
that.
but it looks like the cable's pulling out of it or has pulled
Yeah.
out of it. And then somebody just twisted a bunch of wires together on this other thing and put it looked like a wire nut around it and some tape. Not good. The one on the right here, this is another one of those self-explanatory things that, all right, you need to get somebody in there to clean up that mess. That's almost certainly going to be
Tear it
full of
down.
loose connectors and things that are going to allow signal leakage and ingress to happen. And same thing, upper left here, that's pretty self-explanatory. It's another mess, probably in an apartment building. Um, kind of the lower part of the screen, we can see a cracked cable. And that one, you may not find that one right away. It may not be as obvious because the crack is underneath the jacket. And so that one you may have to get do a little detective work to find out where the
Yeah,
crack cable.
jacketed cable is particularly difficult to see things like radial cracks and any type of like that
Oh, yeah.
damage you're showing there. My experience is people will generally find out with leakage detection because they'll hear the leak coming out with leakage detection equipment before they're actually going to see it underneath the jacket.
Oh, yeah. And then a biggie, loose F connector at the input to customer premises equipment. This is a picture that I took, and I just took a spare cable modem that I had, and just barely screwed the F connector onto the mating interface. And unfortunately, the picture doesn't really show that it's loose, but it is loose. And of course, this can allow ingress interference and other problems. And then over on the right, we see rodent damage to the outside cabling where the things have been chewed up pretty badly. And there again, there's shielding integrity compromised. I love this one in the upper left. Obviously, there was either ingress getting into the plant or leakage getting out of the amplifier. So somebody wrapped the amplifier in aluminum foil and then wrapped that with electrician's tape. If you've got a warped amplifier housing or some other problem that requires doing this, you're probably going to have to replace the amplifier housing.
Yes.
This is not a good fix. This is not. I think we all know that the word temporary is Latin for permanent in cable. And stuff like this, somebody's gonna say, well, I'll come back and fix this later, and it never gets done. And then this thing sits up there for a long time, and it's just a mess. And of course, it's not going to work properly for shielding either ingress or leakage. So this needs to be fixed. Center one, it's another one of those. Yeah, the last tech who was here left it like that. Yeah, right. But you can see the cable pulling out of the connector. The one on the right, pretty self-explanatory. We've got improper connectorization, and that's not good. And then here's another one of those on the left of who needs connectors? Just stuff that center conductor into the barrel on the wall plate. The one upper center is lashing wire damage, or lashing wire clamp damage to the cable, and you can see where the cable and the lashing wire clamp have been rubbing together, and it's actually physically damaged the cable, the shield. So there you'll find a potential impedance mismatch and a potential source for leakage and ingress. The lower image shows tree limb abrasion. Unfortunately, the exposure of the picture makes it kind of hard to see, but in this case, the cable is actually rubbing against the tree limb in that picture, and it's rubbed away part of the shielding and is causing problems. And upper right, that's one of those, wait a minute, how on earth did that happen? And the center conductor is just a little bit long for this connection.
Yeah, but they still made it work.
Somebody
Stick it in
made
there
it work.
anyhow.
Yeah, who did that? Did the tech do that? Did the customer do that? Who knows?
Yeah.
But whoever did it, that ain't right.
Yeah. So we got some stories in the chat here. JazzCat102 says when he first started in cable TV 4 years ago, he ended up finding top of hardline completely gone, including the dielectric. I only saw a copper center conductor about 1.5 feet at mid-span. So It's amazing what damage we can see on the cable. Sean Lester says the rat's nest is every school system telco closet he has been in. So I think he's referring back to that image that you had up of the rat's nest. That's common that
Oh
we see
yeah,
that.
that would be a which one? This one?
Yeah.
This
Yes.
one? This one?
Yeah, you're right. We have lots of. It's so
Yeah, we have
common that we
lots of
see those
examples of
rat's
that. They're
nests.
just the rat's nest.
They're everywhere. And then
It's a,
Matthias says he remembers multiple phone calls in the past with customers that complained of getting shocked when touching the coax connector to the wall outlet. So that's talking about hot cables. So they're
well,
getting shocked on
and
it.
in that case, that can be a hot chassis on a TV set or something, or an electrical wiring problem, and it's using the cable shielding for ground. Because it is grounded, it's supposed to be, but if that's the only path for ground, that's not a good thing, and that could be damaged TV set or some other device, wiring problems in the house, polarity of the electrical wiring reversed. There's all kinds of things that can cause voltage to be present on the drop cable, and when that happens, you really need to get it fixed because it's a safety issue.
Correct.
More than anything else. The upper left screenshot here, this is in the box on the side of a house, loose F connectors. And that's a real picture. I think Nick Segura might have sent me this one. This was one that was found in the field that they checked the F connectors inside the box, and if they're loose, all bets are off. The one below that shows something that was similar to what was described in the chat window, Brady. And this is rodent damage, not as bad as what was described, but here you can see the top of the cable's been chewed away pretty badly, along with some of the dielectric. And I've seen it worse than this, where the squirrels actually chewed down to the center conductor. But here you've got a great place for RF to get in and RF to get out.
As well as water.
Oh, yes, water can definitely get in there. Another cracked shield example in the upper right, and then the lower right's a picture I took at a cable system where I was doing some field work with a cable operator, and we found leakage at this one apartment building, and the bulk of the leakage was coming from this unauthorized drop. Somebody was stealing the service and had connected this drop to the tap, and unfortunately it was causing a big signal leakage problem in that cable system. So this is a common source of problems too. And that's why cable operators need to be vigilant about looking for leakage. You fix the leaks, there's a pretty good chance you're going to fix the ingress sources too.
Fix other problems.
Oh yeah. Now let's talk a little bit about direct pickup interference.
Yeah, just before you start there, a couple more things in the chat I want to get. Sean Lester said regarding the crack shield, a crack manifests small first, which means higher frequencies leak first. As a crack gets larger, lower frequencies start manifesting in the leakage.
Well, and there's something else that can happen too. As the temperature changes, the cable expands and contracts longitudinally, and the size of the crack can change. So the intensity of the field strength can also change over time and temperature.
Yep. True. And then James Long said back at Sean, he says that was a big aha moment for him when he realized that wavelengths are actual lengths.
Yes. Oh, yes.
Good one. Thanks, James.
Yeah.
Thanks, everyone, for the input on that.
Yeah, this is good discussions. All right, what about direct pickup interference? This is what is that over-the-air signals leak directly into a device. It could be a TV set, can be a set-top box, a cable modem, sometimes without any physical connection to that device. Now, how is that the shielding of the affected device is not adequate? So the signal, the over-the-air signal, is coupled to internal circuits via ventilation slots, case seams, and even common mode currents on cables that are connected to the device. We tend to think of ingress as being something happening in the drop or the hardline plant, but direct pickup interference by devices either connected to the cable network or whatever can be an issue too. And we look at a set-top box or cable modem and say, all right, the housing is plastic, but if you take one apart, you'll see that they've usually got a metallic type coating on the inside of the plastic to provide shielding. And then many of the circuits on the circuit boards are also shielded with little cans and things. The problem is that in some of the earlier devices, particularly older CPE, a ventilation slot or a seam in the case acts like what's known as a slot antenna. And RF in the over-the-air environment can be coupled to the internal circuitry via that slot-like antenna, which is a normal ventilation slot or a seam in the device. You can also get direct pickup by virtue of common mode current traveling on the outer surface of the drop cable, and that gets coupled then to the CPE and then enters the device and causes interference. But it's a direct pickup type current. So why is it important? Well, direct pickup can interfere with the performance of the device itself or even the cable service. It can occur to customer premises equipment. It can occur to head-end equipment, some test equipment. For the most part, older CPE is usually more susceptible to direct pickup interference. Newer CPE tends to be much better shielded than older devices. But poorly shielded retail cables and splitters and other things can offset the benefit of good CPE shielding. So you might have a newer CPE in there that has really good shielding, but if the customer puts in their own pieces and parts, all bets are off then, and then the stuff can get into the network. Interestingly, the cable industry discovered when LTE services started to be launched that some head-end equipment and some test equipment was susceptible to direct pickup interference. And I remember seeing on some cable grade spectrum monitor or spectrum analyzer equipment being able to pick up LTE signals without anything connected to the analyzer, and even with the analyzer input connector terminated, it could still see it. Well, that's a function of the test equipment. That just indicates shielding not as good as it could be. And I remember an instance with I think it was a downstream laser in a head end that was getting interference, direct pickup interference from a cell tower that was next to the head end building. And of course, when I heard about it, I asked the question: was that made by the company I work with?
Was it a feature?
Yeah, and I was told, no, it's not yours, it's a competitor's. And the manufacturer had to come in and do some on-site upgrades to the downstream laser with conductive tape and other stuff to improve the shielding integrity of the head-end equipment. So direct pickup interference can get directly into these types of things, and it's important to understand that. If you experience that, work with the manufacturer of the affected equipment.
Yeah, it's an engineer's nightmare for those manufacturers.
The whole thing, you get into the world of what's called EMC engineering, yep. Electromagnetic compatibility engineering, and it's a mix of science and magic, I think.
It is really, I've been on that side of it, and it's really tough to keep these signals
it is
contained.
Tough. I remember touring Cisco's EMC lab one of their labs on the East Coast, and they had great big anechoic chambers for measuring RF shielding of devices and also susceptibility to interference. So they would blast it with just high power RF signals, yep. With real strong field strengths in the anechoic chamber. And then the lab where they would do fixes, these guys were working with finger stock and conductive tape and other stuff to try to fix the shielding, in a lab environment. And then that would go into production as production upgrades to the products before they ever hit the street. So it's a real science, and it's one of those things that I thought, that would have been fun to work in. But anyway, we have reached the end of part one of this presentation. We've got, I think, a few minutes left for any questions or comments.
And I think we have a couple more comments in the comments section there. So Sean said, leakage detection also finds non-paying customers. So that's an interesting thing, because
that's true. And that goes back to that example of the unauthorized drop at an apartment building that I snapped a picture of. That was causing signal leakage, and we were there looking at other stuff, but we found this leak. Oh, hey, cool! Look, here's somebody stealing service. They're not paying for the cable service.
Yep, and that's so that's something else we found with proactive network maintenance. I think we've covered that in our Cable Labs calls at PNM, because the act of like inserting, kind of like you showed that one image where there was a bunch of coax cables, drop cables, kind of just stuffed in without having terminations on it. That is something that'll light up a proactive network maintenance system, because you have a bunch of impedance mismatches there. And then we see that the same thing with customers, and that'll just take like a penknife and stick it into a hardline cable and stuff a drop cable in that will also, like any kind of damage to hardline cable. Proactive network maintenance is really good for finding basically theft of service. So anything that's basically disrupting the cable network like that. So
Oh
good
yeah.
comment on that, Sean. And Sean says he says I've seen that LTE interference, or I've seen that LTE interference. I think the one image you're referring to, but it was usually loose connectors at the laser input that was causing that.
Yeah,
So
the one that I was referencing was not the input connectors to the laser. It was the chassis itself that had issues.
yeah.
The manufacturer actually had to get in. They had to modify the chassis. It was not the connectors in that case.
And
That
I've seen, so I
the
think, kind of tying on to Sean's comment with the LTE, since we've been doing a lot with RxMER on OFDM, OFDMA channels, I've seen a lot of areas where the RxMER will be degraded for the entire node. And it almost always goes back to, is that node set up correctly? And if it's not, you end up with, basically non-ideal signals coming out of the node. Your RxMER per subcarrier is degraded for all your channels, and then you're trying to figure out, well, why are the subscribers not getting gig service? And it's because they're
Yeah.
running on the lowest profile for that OFDM channel. So we got to go back and rebalance the node and get everything running for that. So James Long says this is pertaining to in-home ingress, and I think we'll talk maybe just a little bit more of that, but we have a DOCSIS channel that almost always has at least some corrected FEC code words, and I'm fairly sure it's from LTE handsets in the home.
That's possible. Yes, that is possible. The cell industry calls it UE, or user equipment, and that would include cell phones, the smartphones, tablets, and other things that use cellular frequencies, and they transmit on the uplink frequency band. And yes, the signals from user equipment can get in to the cable network through the subscriber drop or in-home wiring issues if they're loose connectors and other problems. And if you think about it, the field strength that's close to the UE can be rather substantial. I had done some calculations several years ago, and I don't know if we put that in an SCTE paper, or I think it might have gone in an SCTE paper. It calculated the user equipment field strength just 1 meter away from user equipment, and the field strength produced by that is insanely high. I want to say it was up in the million microvolt per meter range, something like that. This is like 1 meter away from the cell phone, transmitting at maximum power. So yes, in-home interference can occur, or can come from cell phones and other user equipment.
Yeah. All right. We'll take one more question or comment or question. It's from Sean. He said, I had the chassis issue too, but it was with a digital video product from one of Ron's competitors. So we'll mention who that is.
Yeah. Those things happen. The industry learned that equipment. I mean, in the past it wasn't a big deal, but when you start putting up cell towers next to head end buildings, and then the LTE spectrum starts to fill up with signals up in the 600 to 800 megahertz range, it's okay, that was an issue nobody anticipated.
Yeah. So Ron, I think you had a nice representation of like images of impairments from both outside plant and in-home plant, but I think kind of said 95% of the issues for ingress come from subscribers home, and that's kind of my experience. Like when I see damages and stuff, or when we're doing repairs, it's like drops, in-home wiring, bad connectors, reverse splitters in subscribers home. And I just kind of want to ask from you, if we were to kind of lay out what would be the most damaged or what would be the most problematic things, would you agree it's going to be subscribers in-home wiring that's we're going to be looking at?
I would say that that's certainly a substantial percentage of the sources of problems is the in-home wiring, and there are a number of reasons for that. Of course, one is potential craftsmanship issues. But if you think about the in-home wiring for the cable network, once the installer is done, and let's assume that it's done properly, everything, tight connectors, everything's done right, we have no control over what the subscriber does. The subscriber might say, I'm going to rearrange the living room furniture and move the TV to the other side of the room. Oh, rats, I don't have enough cable, so I'll go down to the big box store and get some, and I'll put my own connectors on it and try to extend the drop to reach that, or they'll disconnect things because they're moving things around. They're going to paint the walls, so they disconnect stuff and they put it back together and don't bother to tighten the connectors the way they're supposed to. There are any number of things. Or they buy the retail grade stuff and install that. That's a big no-no. Maybe the dog chewed the cable, or who knows. Things can happen once the cable company personnel have left the premises, and we really don't have any control over it.
Perfect. Thank you. So I guess a couple of comments come in from Matthias. Theft story. Oh, these are good. A landlord paid for one residential unit in the building, split the signal into all apartments. He rented the complex himself and collected monthly payments from all tenants himself. So yeah, he was making some money.
Yeah, and probably causing leakage and ingress too.
Yeah, a great source of extra revenue for the landlord there. So, and then Ray Stevens does the size of the crack in shielding affect the possible ingress frequencies?
Yes,
I think that's a good one.
But there's some other things to keep in mind too. You can have a crack or a loose connector or something that could be the potential source of ingress, but you need over-the-air signals on certain frequencies to be the source of interference. So if let's say you've got a subscriber drop with a loose F connector out of the tap port, and there's nothing around, there's no over-the-air noise, there's no two-way radio, no FM radio, or nothing. Well, there's nothing to get in. So you can have a loose connector, but nothing's getting into the plant. Of course, the real world is the stuff's going to be there, but imagine a ham radio operator transmitting with the legal limit of 1,500 watts, 50 feet from your loose F connector. What's going to happen? That's going to blow away your upstream. And the problem is not the ham operator. I'm a ham and have been for a long, long, long time. The problem is that loose F connector. But if the ham operator is not there, maybe there's just a little low-level ingress getting in through that loose F connector. So the intensity of the ingress really is related to what's present in the over-the-air environment. And particularly if there's a strong signal source near the ingress point, that can really cause big, big problems. Even though you might go out there and measure leakage and, there's not much leakage here. But you got a 1,500 watt over-the-air signal 50 feet away. Yeah, that can cause a big amount of interference.
It sounds like the analogy to this: if a tree falls in the woods and no one's around to hear it, does it make any sound? But maybe not. Sean says, what's the old saying? Customers are liars? I don't know.
Well,
DR, the area you are in, heavy over the air or not? And I think he's just, agreeing with what you're saying there. It's lots of over-the-air traffic. Your leaks are going to be more problematic for the cable operator.
Well,
if there's not.
The leakage can interfere with those services, but those signals can leak in and interfere with the cable company's services.
All right, Ron. Once again, amazing material, folks. There you have it. Another enlightening episode of our Back to Basics series on DOCSIS and broadband has come to a close. Today's journey on Ingress Intrigue has been both informative and engaging. I'd like to extend a heartfelt thank you to Ron Hranac. Ron, your expertise and insights are always invaluable, and our audience is, as well as I, greatly benefit from your vast knowledge. So thank you so much.
To help. And we'll do part 2, I guess, next month.
Yes.
There's more, but wait.
It's coming up, and I'm going to give you the date in a second. To our viewers, thank you so much for tuning in. Thanks for everyone in the chat room for the chat. Hope you found this episode useful and enjoyable. Be sure to join us back on September 15th for part 2 on what to do about ingress with yours truly. Ron and I will be back for more. Ron already has the presentation all queued up and ready to go. Please remember to like, share, subscribe, and stay updated on the series. Drop your questions and comments below. If you didn't get them in the chat, who knows? Your question might be the central theme of one of our upcoming episodes. So until next time, everyone, take care and so long.